Hello, my group is pleased to present our project, CookIQ, a tool designed for home cooks to decide what meals to make based on their preferences, spice up their meal routine, and join a social community aimed at improving the home cooking experience. First, let me introduce our team. We have John, myself, Cullen, Keegan, Jack, and Josh. Each of us come with different levels of expertise, which has allowed us to work collaboratively throughout the year to build an application. Front-end and back-end development created the core structure of the application. UI and UX design and business strategy helped us create a useful and relevant tool for the user. And artificial intelligence and data science allowed us to integrate smart recommendations that are customized to each user based on their preferences. So, what problem are we trying to solve? We are trying to solve three common problems home cooks face when trying to expand their recipe repertoire. Firstly is choice overload. With unlimited options, it's hard to know what you or your family will like and which option to choose next. Second, home cooks have competing priorities, trying to balance nutrition, cook time, calories, the number of proteins, and more. It's very difficult, especially when you're cooking for a huge family. Last is uncertainty. Oftentimes, we just choose recipes that we are familiar with, which only reinforces the cycle and leads to repetition throughout the week, further making it difficult to spice up your routine. So is this a problem that people are actually facing? Well, yes. A recent study by HelloFresh found that 85% of Canadians want to cook at home, but it is actually a rare occasion. A quarter of Canadians know 5 recipes or less off the top of their head. That's not even enough meals to fill a whole week. Half of Canadians indicated that they wish to eat a more balanced diet, eating at home more often and introducing more vegetables. With CookIQ, we're aiming to tackle these commonly faced problems by introducing new recipes that are custom tailored to each user with our AI recommendation engine. Looking deeper into how we actually plan on solving this problem, first we have a custom onboarding phase for each user in order to get a sense of their palate. We then provide custom recommendations using our a priori and cosine similarity engine. Once the user starts making recipes, they can post to the feed and also follow their friends who are also in the app and see what they're cooking and if they've liked it. Lastly, we have an LLM chatbot to answer questions the home cook may have about the recipe or to discover new recipes. So let's actually look at a journey through a user's eyes. So let's meet Joanne. She's a young professional and she's trying to cook at home more often. So first, when she signs up, she'll rank some dishes in the onboarding phase to define her profile and her palate. Next, she'll get a set of recommendations which she can choose a dish and cook it. She'll observe the ingredients needed, follow the steps, look at some pictures, see if she's doing it right, and once she's cooked it, she'll give the dish a rating. Either she loved it or maybe she hated it. Optionally, she can post to the feed and also see what her friends have started cooking, if her friends are also on the application. This journey will be cyclical, as feedback from each meal prepared will be used by the engine to drive future recommendations. So if you started cooking Mexican food and you really like Mexican food, the AI recommendation engine will probably recommend some more, or maybe something new to spice it up. Now, let's dive deeper into the actual application.
Great, thanks, Sam. Now, before we get into the application, I'd like to briefly explain our authentication process. We used Amazon Cognito to handle user authentication and for user management. So after each login, it returned a JSON web token and a user sub. These were both saved in local storage after the user logged in for easy access later on throughout the application. This user sub was used as a unique identifier for each user in the database. While the JSON web token was used for authorization, it authorized database operations for protected routes, and it also provided continuous session management. So that was a little bit about the authentication process. Now let's check out the application. So this is the CookIQ login page, place to sign in. But as a new user, we need to first create an account. So we'll sign up, enter a name, last name, enter an email, password. Password does have password requirements that need to be met. So let's make sure we do that. And we can sign up. So after a user creates an account, they need to verify their email to ensure that it's the correct email that they want to sign up with. So just received an email, their code. So once we do that, we can verify this code and our account should be verified. So we should now be good to log in. So again, I'll use the email to sign in and the password. So since this is a new user, we have to first go through an onboarding process to begin our CookIQ journey. Uh, so this onboarding process requires us to rate a number of meals. There's 5 of them. It shows the recipe description, the name of the recipe, and a little photo to describe it. And we can see that we can rate the recipe down at the bottom here. So there's 5 recipes to rate. We don't have to rate them all, but let's say we don't really like this one too much, so we'll give it a 2. There's banana bread, like banana bread, so we'll give it a 4. This one we'll give a 3.5. So you don't have to rate them all. So once we're done, we can press done, and then this will begin our recommendation engine based on these onboarding process, which Johnny will get into a little bit further. So right here, we can see that you can manage the user even further on the settings page. You can see there's first name, last name, email that we put in, and we can also upload a profile image. So we upload a profile image, nice baby loon. So we can see that the profile image is updated. We refresh the page, the profile image updates over there too. This enable public profile will be talked about a little bit later on in our social feed when we get into our social feed. But for now, that's all. So I'll pass it on to Johnny to talk a little bit more about our recommendation engine.
Awesome. Now we're going to talk a little bit about how the recommendations for CookIQ works. As we can see here, there's a mock-up containing a variety of different recipes down below, along with some additional context. So first things first, personalization is key here. The recipes that are recommended to a user are based on the initial ratings that Colin went over, ranging from 1 to 5 that were given during the onboarding process. These dictate what the initial recipes that users see after completing onboarding are. Following that, there's also an adaptive element whereby the ratings, or recipes rather, that users rate build into a more comprehensive picture of what that user likes, and in doing so, provide more tailored recommendations to them. Finally, there's an update component whereby as more data is logged, not just for a single user, but for all users of CookIQ, this data is stored in our database and on a daily basis. The a priori rules, which we'll get into in just a moment, underlying the model are updated to find new relationships and patterns based on recent user data. So let's chat a bit about how this recommendation engine works and what the key components are. The unified recommendation engine, which is number 3, is built from 2 components, a cosine similarity table and a priori rules. The cosine similarity table essentially calculates, based on a variety of key features, which we'll get into in just a moment, the similarity between different recipes and puts those into a 10,000 by 10,000 matrix, each cell of which contains the pairwise score for those 2 recipes. This is amalgamated with a priori rules, which utilize the a priori machine learning algorithm, a type of association rule learning, that derives a set of rules for related recipes that have surpassed a certain set threshold for the strength of the relationship to one another that are set in the code. Both of these come together to produce the unified recommendation engine, which combines both components to create a system whereby users can see what recipes are best suited to their tastes. So let's talk a little bit about each one of these components. The cosine similarity table takes place through 5 main steps. The first is vectorization. This is where we take the language and turn it into a numerical representation that can then be calculated to produce a similarity score. Next, we create matrices based off of this. This was done so for 2 main features, the ingredients list as well as a recipe name. Then those 2 matrices for the ingredients list and recipe name were combined through matrix addition, whereby 70% of the weight was allocated to the ingredients list and 30% to the recipe name. And this was done with the intention of focusing more so on the ingredients of a dish rather than just its name. From there, to avoid having to store a massive file, 10,000 by 10,000 entries, we simply took the top 30 most related recipes for each ID column to produce a data frame that is then used for our recommendation engine, which was exported as a pickle file. For the a priori rule set, this was done through taking the interaction data from food.com, creating a 2-column data frame that has the user ID, as well as the corresponding list of dictionaries of all the recipes they've ever rated and that corresponding rating. For any ratings that were given above 3, these are sub-selected and treated as having the user enjoyed them, the user having enjoyed them rather. And then which the a priori algorithm is applied through setting limits on confidence, support, and lift to determine what rules emerge from patterns. Say, for example, a user who likes making burgers might also like making pasta, or vice versa. These rules are then exported as a pickle file as well for ease of storing and permissioning with AWS services. And then all of this comes together to produce our unified recommendation engine, where we'll get a recommendation ID as input that the user has just rated, search to see if there are a priori rules that match the given recipe ID. If there are, we'll start with using those because they are what we call collaborative filtering. And if there aren't, we'll go directly to the cosine similarity table. If there are less than 30 a priori rules, which is the amount of we ultimately want to return, then we'll backfill the remaining with the cosine similarity table to produce and return recommendations DF, which contains 30 recommendations. So let's see how this works on the front end. So let's say we are Cullen and I've logged in. We've gone through the initial onboarding process. Now we see the recipes. I can click on these recipes and rate them correspondingly. And once I submit, we see the match percentage here. That rating is saved. And over time, the recipes I get will start to update based on how I rate these. And with that, I'll pass it on to explore the next feature.
Now I'll be going over the feed and the bookmarks tab. And right now I'm starting on the recommendations page to show how we can actually bookmark or unbookmark something. So we currently have the flourless banana bread bookmarked, and we have the banana bread muffins unbookmarked. If I click on that, that will remove the bookmark, and that is removed. And then I can click on the bookmark feature for banana bread muffins. This effectively saves the state in the database saying that the user is affiliated with this post. Finally, when I go to the bookmarks tab, I can see that the banana bread muffins are there and the other recipe is no longer there. Next, if we go to feed, we actually have some pretty neat features. So for one, all of the users are incognito, as Colin mentioned. And here I can decide who I want to follow or unfollow. So as you can see, I'm currently following Cullen, and that is why all his posts are here. As well, I'm following Keegan. So I keep scrolling, I can see all of Keegan's posts. Next, if I want to, let's say, unfollow someone, and then I can click the unfollow button. And if I reload the page, then his posts will no longer be there. So you can, as long as the user is public, then you can see their posts. And a post is effectively on the recommendations tab. If I'm rating a meal, when I rate the meal, then I'm effectively posting about that meal because I've enjoyed it and I want my friends to see it. Next, we have a little bit of a neat feature in the like. We use something called debouncing, which I'll discuss a little bit more later. And for now, this is the total number of people who have liked it. These are the number of unique users, and I can click it a bunch of times in a row in order to improve latency. It only acts on the last click. So I've now unliked this post, and maybe I want to unlike the top one as well. I'm not a fan of these banana bread muffins. They're not as cool as I thought they were. If I reload the page, the state is all saved, and the previously liked ones are there as well. So those are the gist of the features. I'll go into a little bit more technical details. Now jumping into a little bit of some of the optimizations used for the social media feed and the bookmarks. First, we started with reducing on the feed, actually the run times, the latencies of actually loading the feed. Initially, we came across the issue that it would take about 10 seconds to load the feed, and we reduced it down to 3. And we did that through SQL query optimization. So on the left-hand side over here, you can see that it actually goes through 3 joins, and that'd be an O of n cubed. So the entire recipes table, the recipe tags table, and the recipe IDs table, and the tags table. Those are all the tables that we needed to actually get all the data in. But instead here we have a join here, and we have a pre-select, we have a subquery here, and that makes it run into O of n. So this is O of 1 times O of n, making it O of n, and then we add that with another O of n operation down here to get the recipe ID, and the recipe tags. So joining those many-to-many relationships, and that's how we reduce the runtime there. Some unique skills that we gained were one was debouncing, and that's just when you're clicking on something a bunch of times. If the space between the clicks is short enough, you want it to only run once for the total accumulation of those clicks. So we implemented that as debouncing, and it would only click 300 milliseconds after you click on the like button per se. So that'd be the like button or the user search. And that way we reduced the latency so that it wouldn't be calling our backend too much. Next, we had the regex search, and the regex search was responsible for actually looking up the users and looking at the feed there. So there we did the start. We dealt with the starting of the user or the initial characters on the search tab, and we were deciding between that and the whole length of characters, or just like looking at every single section. And in order to reduce latency, it made more sense to just do it with the start. Finally, we did a database redesign, and that was because we couldn't initially identify which users liked which post. We just had the total likes. So we had to make another like post table to actually see which users liked it and to store the previous state of whether or not the user had already liked the post.
Hi there, my name is Jack, and today I'm going to be telling you a little bit about our custom LLM food question bot. Here's a UI of what it looks like that I'll be showing you in the demo shortly. The first thing that we needed to do to create this demo bot was to make a vector database of the recipe titles. The reason why we needed to do this is because if we just simply fed in all of the recipe info into our LLM and asked it a question, there's too much data for the LLM to actually interpret this. And this is known as the context window of the LLM. And so for this reason, we used a vector database, which creates a relationship that indicates the possible similarity of words consisting of the recipe titles. And then we did a similarity search on that with the user query. From this query, we then get the recipe title that most likely matches the query of the user. And then we get the recipe info for that specific recipe title. And then using that recipe title, we then feed that in with the query to our LLM and then ask it to generate a response based on that information. The technologies that we used for this included Phase, which is a vector database built by Meta, LangChain, which connected all of these various components, and Cohere, which is our large language model provider, and also created the embeddings that we used for a vector database. And the embeddings are just simply the actual mapping of the relationships between the words. So without further ado, let's take a look at our food chatbot here. So if I say, what is the third step in the Asian slaw salad recipe? I ask the chatbot. It's going to think for a bit. And then it's going to say the third step is to toss all salad ingredients together and then toss with salad dressing. And so you can ask it a variety of questions like this, and we hope that this would be useful to our users. Thank you.
All right, awesome. So let's jump into our Capstone infrastructure now. So we'll do a little high-level overview of each of the components and why we made the decisions to actually go that route. So we'll start from the bottom. You can see that we divided our code into different repositories for different functions. The front-end repository, obviously containing our front-end code. We built that with TypeScript, React, Material UI as our UI framework, and used Axios to serve as our package manager for any of our requests. Additionally, with this repository, we added a GitHub action pipeline. So what that meant was any PRs being made merging onto the main branch would trigger a set of steps. So for us, that meant it would be triggering a linting check and then also running npm build to actually build the static assets of a React application and then push those directly into an S3 bucket. So Amazon's S3 is their object storage. It can replace any existing assets that are on that S3 with our new assets, and then allow a client to publicly access that URL of the bucket to get the resources. So essentially how a website would work. For our backend, we used, again, another repository to write that code using Express.js, Jest, trying to use MVC architecture as well, so separating out our view onto our front end with our React, and then our models and controls were written in separate files on our backend. This repository also had a GitHub action pipeline. So for those steps, it included unit tests. So again, using Jest, we ran unit tests to make sure our code was working all together. And then also creating an image So we create an image based on the code in the backend repository, and we push that to Amazon's Elastic Containers Registry, which is their hosted image registry automatically whenever branches were merged in the main branch, replacing that latest tag every time. What we could do with that image that was then existed in the registry was actually run it on an EC2 instance. So we deployed an instance of EC2, and then we could actually go and fetch, so pull that image from the repository, install Docker on the EC2 instance, and then run that image. So it's again serving as our backend. Since the EC2 instance would often change its IP address, we added elastic IP address, so essentially a static IP address in front of that EC2 instance and attached to it. So the S3 bucket that held our React app had a static base URL that it could reference for any of the endpoints it wanted to interact with. Again, as mentioned from Cullen, we use Cognito for JWT authentication and authorization. So any request going to protected routes, we would verify with Cognito first that the token was valid with middleware, and then send those requests to any other possible resources. We use Amazon's RDS to host our Postgres SQL table, which was pretty straightforward to deploy. And we'll talk a little bit about the actual database design in a second. Onto the really fun stuff, the recommendation engine. So all the code for this was written in Python, so we couldn't directly put it into our backend repository. So we had to have a new solution, and we decided to go with Lambda functions, so serverless functions from AWS. These were great, but they had a restriction on the amount of packages that could be installed. So packages are treated as layers, and there's only 250 megabytes, and some of our applications that we were writing required packages that were bigger than that. So we had to come up with a new solution, which was back to our good trusted images. So we used to create an image based on the code we wrote, push that to ECR, and then build the Lambda function and execute it based on that image. Any associated pickle files, so like as Johnny mentioned earlier, those a priori rules or cosine similarity tables that we needed to pickle, we could put into an S3 bucket and then fetch that from a recommendation model. To make the code a little more dynamic, we added another Lambda function to update the rules. So we could trigger that Lambda function with Amazon CloudWatch. So every day we could run, which was triggered by a cron job, that update pickle function. So it would kind of go through the data and activity on the day, create new sets of a priori rules, append to it, and then replace that instance of that a priori rule pickle in our pickle S3 bucket. So future recommendations would be grabbing the updated pickle. That Lambda function was exposed through an API gateway. So we had a REST endpoint made, which was connected to it. So we could fetch any recommendations we want based on APIs through that gateway, which would trigger the recommendation model to give a response. Our LLM was deployed in a similar manner. So again, we were using Python, so we had to put it somewhere else outside of our backend repository. We chose to do the same sort of route where we pushed it to an ECR, built a Lambda function based on that image. It connected with Cohere for any of its responses based on our query. And then we put a REST API with Amazon's API gateway in front of that, so we can make a request directly to it from our EC2 instance. So into our database design, fairly straightforward. The client table reflects the connection between our RDS and the Cognito, so using the user sub as the ID. Recipe was our raw subset of data we wanted. So this had all the sort of general principles and attributes of any recipe we wanted. The meal table represented any interactions between a client and a recipe. So whether that's bookmarking a recipe, rating a recipe, or cooking a recipe, there would be a new entry made in the meal table to reflect that activity. And then upon cooking, we would have a post. So that activity would be triggered the creation of another entry into our post table, which would automatically record the timestamp of the post, along with then the user ID and recipe ID, which would be put into it. Like post followed a pretty similar manner. So this was used just to kind of connect clients to posts, and followers had another table with a follower ID and a user ID, both being client IDs, just searchable through the user tag. So a property that exists on Cognito. Recipe tags. So the tag description had a many-to-many relationship with recipes. So we made a recipe tag table to kind of separate those two. And I think the relational database structure worked well for us for this project because of our sort of complex queries. So whether or not we wanted to fetch a feed for a user based on the followers they followed, that turned into be more complex. So the relational database sort of supported that, as well as any sort of recommendations we wanted to do, where after we got recommendations based on their meals that they used before, we wanted to join on the details of those meals and get tags associated with recipes. So this database allowed us to do just that. That's all we have for today. Thanks so much for listening to our presentation. We really appreciate you taking the time to do so. From everyone here at CookIQ, we want to say thank you, and we hope you have a great rest of your day.